Good evening, everyone, and good morning. So today we have with us Professor Hema Yoganarasimhan. We are very privileged to have her with us. I'll just quickly introduce her. So Dr. Hema Yoganarasimhan is a professor of marketing at the Foster School of Business, University of Washington. She also holds affiliate appointments in computer science and engineering, Department of Economics and Center for Statistics in the Social Sciences. She serves as a co-editor at QME and as an AE at Marketing Science and Management Science. She is recognized as one of the leading experts in quantitative marketing. Hema's research brings together large-scale marketing data, econ theory, and econometric and machine learning tools to help firms optimize and automate their marketing decisions. Our recent work focuses on combining machine learning tools and statistical econometric methods to address important problems in the domain of digital marketing and online platforms. Her one stream of research focuses on targeting in mobile and online advertising, how to target ads at scale using personalized user theory, history, and how can we quantify the optimal level of targeting from a platform's perspective. And in another ongoing project, she develops methods to personalize search rankings on online platforms in real time. Hema's research has won many prestigious awards, including the MSI Clayton Doctoral Dissertation Proposal Award, Frank Bass Outstanding Dissertation Award, John D.C. Little Best Paper Award. She has also been recognized as a MSI Young Scholar in 2015, an MSI Scholar in 2020, and also Erin Anderson Emerging Female Marketing Scholar and Mentor in 2021. She received her PhD, MA, and MPhil in Marketing and Business from Yale School of Management. Prior to that, she received her bachelor's degree from Indian Institute of Technology, Madras. She has been at University of Washington since 2014, where she teaches MBA and undergraduate classes on analytics for the 4 Ps of marketing and an advanced PhD class on dynamic structural models. In short, Hema is a titan in the field of quantitative marketing, I'll put it that way. And we are very pleased to have her with us. Thank you so very much once again for taking out time. Without further ado, I'll hand it over to you.
Thank you so much. Thank you, Anish, for a very kind introduction. I have to say I'm very excited about giving this talk. IMA is the leading business institute in India. And even when I was in college and so on, almost everybody wanted. In IIT after that, always wanted to take the exams, the CAT exams for IMA and be there for MBA. And also I know some of my friends have been there for doctoral studies. So I'm very excited to be able to give a talk with your group. So without further ado, what I wanted to do is jump into the talk. And as I would like to say that if you have questions, clarification questions or anything, please feel to put them in the chat and I'm happy to answer them as we are going through. So today I'm going to be talking about ranking I would say how we think about inference when we are talking about algorithms for ranking experiments and whether these inferences would be biased in standard settings and how they would be biased and how we can fix them. And this is joint work with my colleague Ali Goli, who's also at UW, and Anya Lambrecht, who's at LBS. So let me start by giving you a little bit of quick background on ranking algorithms and digital platforms. So ranking algorithms, as we all know, are at the core of digital marketplaces. And there are many examples of digital marketplaces that we know which we use ranking algorithms, things like Airbnb, Amazon, Expedia, Instacart, TripAdvisor, anything that you think of, where users essentially come to the website and enter a query to search for something, and then they are shown a rank-ordered list of items. And these rank-ordered list of items could be things that the platform itself sells, for example, in the case of Amazon, or it kind of sources from multiple parties where the platform is kind of a matchmaker, something like Expedia, for instance. So it doesn't matter which type of platform it is. Essentially, the platform is doing the ranking over a set of products. And these kind of ranking algorithms, at least almost all these firms strongly believe that they have a pretty big impact on user engagement and platform revenue. What I mean by that is that if I search for, let's say, flights to place X, and if I get some kind of ranking, that's going to have a big impact on what I click and what I actually book at the top. So these platforms are very concerned about making sure that what they show in these ranking results are actually relevant and actually have a big impact on what users will click and therefore their eventual revenue. So their goal often is to pick what we call the best ranking algorithm, and among a set of algorithms they might have at their disposal, and then deploy it at the platform at large. So they usually have large data science teams or engineering teams which continually work on these algorithms. And what their goal is often is to keep improving these algorithms and then try to pick the best one among a set of, you might say, front runners. And when they're doing this, their goal is to measure what the performance or what the overall, you might say, click-through rate or revenue or whatever the metric of performance is, how that would change or what would that be if all the users in the platform were assigned to this algorithm. And that's what we would call the total average treatment effect, and which I'm going to shorten a state throughout this talk. So what is the practice, the standard practice for identifying the ranking algorithm? So the standard practice is to run an A/B test or a field experiment, whatever you call it, and estimate the take for each algorithm on an outcome of interest, and then pick the winner. And the caveat with this approach, or in some ways A/B test, is that the performance of this algorithm of any of these algorithms which we are testing is observed under the A/B test, where a random subset of users are assigned to it, and not when it is fully deployed. What I mean by that is that if I just have two algorithms and I send half the traffic to each, what I'm observing is essentially the performance of both of these algorithms when half the people are assigned to it, not when I would scale it up to the entire platform. And for this to be valid, this inference to be valid, what we really need is the standard Sutwa assumption, where outcomes under one algorithm are not influenced by other algorithms or treatments. So the question then is, are A/B tests of ranking algorithms valid? Is somehow the Sutwa assumption valid here? And when people think of assumptions of the Satwa violation, they often think about things like social networks or something where it might be violated, A/B tests at the individual level. But what I want to do now is walk us through a very simple example where I'll show you how even in a very simple setting, the Satwa assumption for ranking algorithms, A/B tests of ranking algorithms, is very clearly violated. So here is a very simple example. What I have is, let's consider a platform which has 3 hotels, which lists 3 hotels. Let's call these hotels A, B, and C. And each hotel has two rooms. Let's say the hotel just has 2 rooms, one high price room and one low price room. And you can see that here. And then let's assume that the platform wants to test 2 algorithms. One algorithm, let's say, lists A at the top, B in the middle, and C at the bottom. And the second one just flips the ordering. It's going to be C, D, and A. Now, in terms of how users behave, again, as I said, I want to just highlight the basic problem here. So let's have a very simple user model where let's say that when users come and are shown some hotels in some rank ordering, they always click if the hotel in position 1, they click with probability half if a hotel is in position 2, and with probability 1/4 if a hotel is in position 3. And conditional on clicking, if there is a low price room available, let's say they just buy it. If there is a high price room available, they buy it with probability half. So this is how the users behave. So our goal now is, and suppose there are just 2 users on the platform, and we can have an A/B test where each user is assigned to 1 algorithm each. And our goal now is to estimate the total average treatment effect of algorithm 1 under the A/B test, as well as when it would be fully deployed, and see if these match. So that's kind of the goal. So let me start by just looking at the total average treatment effect for of algorithm 1 when it's fully scaled up, which means everybody is going to be assigned to this algorithm. And this is the number we are truly actually interested in, because that's what the platform wants to know. If it were to move to this algorithm, what would happen, right? And in this kind of a scenario, let's look at the demand for hotel A under algorithm 1. So what happens, everybody is going to be shown hotels according to this algorithm. So user 1, the first user comes, they see in this rank ordering, because they'll always click at the very top hotel and the position and will buy with probability 1. If there actually is a low price room, the expected demand for hotel A here is going to be 1 from this user. So they're going to buy that. Now, when the next user comes, remember when it's fully scaled up, what's happening is that this low price hotel is no longer available. This person still clicks hotel A with probability 1 because it's still at the top, but now only the high price room is available. Therefore, the probability of purchasing that room is half. And what that really means is that the expected demand per user for hotel A when algorithm 1 is fully deployed is 3/4. And what you can see here is that when the algorithm is fully deployed, the distribution of prices that these users are seeing is skewed higher because the second user is not seeing the low price anymore. So the distribution of prices is skewed higher. As a result, the demand is lower than 2, for instance. Now let's see what would happen if you actually didn't deploy it, but instead did an A/B test where half the users got one algorithm, the other half got the other. So there can be 2 scenarios, user 1 gets 1 and user 2 gets 2 and vice versa. And what we are interested in is the expected demand per user under algorithm 1, right? So we are always interested in this one algorithm. So now let's look at scenario 1, where the first user gets algorithm 1. What happens is that the expected demand for hotel A is 1, and the next user is going to get algorithm 2, so it's irrelevant. So in this scenario, we kind of see that the expected demand per user for hotel A is 1, because we never see the scenario where the low price room is unavailable, only high price rooms are available. Right? Because we never get to, because it's only deployed on half the population, the supply constraint is not kind of going into effect in some ways, right? So in some ways, this lack of this low price room is not even observed. So we extrapolate the demand from here, we would just assume that the overall demand per user is 1 rather than the 3/4, which we saw previously. And you can do the same analysis for scenario 2, where the first user gets 2 and the second user gets 1. It's similar, it's slightly different, but it's again inflating the demand. It's 7/8 and not 3/4. So overall, what we see is that when we have this kind of an A/B test, the prices of hotel A under algorithm 1 appear to be lower than in the counterfactual world when it's fully deployed, right? Because think about this as a case, for instance, there is a small hotel with few really low price rooms and a bunch of high price rooms. When I run an A/B test where I have deployed this A/B test on a small population, it looks like this hotel is going to do very well, right? Because few users see the low price, they buy it, it looks great. But now when I take it to everybody, the few low price rooms are going to be sold out, and they're only going to be these high price rooms, and people are not going to buy it. And that's because essentially the other algorithms were kind of suppressing the price, right? Half the price was in some ways, like the supply constraint was slack as a result. So as I write here, so in some ways the A/B test, the algorithm 2 is demoting hotel A and making it less likely to run off these low price rooms. So there is an interference effect of where the hotel is ranked in other algorithms affects the distribution of prices that we see in the algorithm of interest, and therefore the demand for that. And that's kind of the main idea. So if you actually work through this example in full detail, which I didn't want to do because I don't want to make this more tedious, is you'll see that for Hotel A, the demand under the A/B test is inflated compared to what it is in reality, whereas for Hotel C, it's it's the other way around. It is underestimated because it is the other hotels are kind of making the price constraint look more slack, whereas Hotel B, which was in the middle, you'll see that the demand for that is essentially neither underestimated nor overestimated. It's exactly the same as what it should be. So, and the reason is because this hotel is ranked the same under both algorithms. So there is zero interference between the algorithms. And the estimated demand or take, therefore, is unbiased, which means that in the world of the A/B test, B is always in the middle. In the world where one of these algorithms is fully deployed, it's also always in the middle. So it's what its average position is in this world is what would be in the counterfactual world where everything was deployed. And therefore, we would be able to correctly estimate its demand. And this is a key insight. And this is the main insight that we will use for our solution later on. And Hotel C, I already talked about it. So because it's promoted by it's demoted by the other, promoted by the other algorithm, again, we are kind of underestimating this. So what I showed in this example was one source of interference bias, which is that the supply side constraints, right? Where if you have only some number of rooms, then what happens to what happens to this? But you might say that not everything has hotels obviously, have hotels and airlines obviously have supply side constraints, but not maybe products on Amazon, for instance. So even in those cases, though, there will still be problems, what I would call interference, if there are strategic responses from sellers. So the way to think about this, a very simple way to think about it, let's say that I run an A/B test where I have one algorithm where I pick a new small seller and show them at the top, they have some demand. Right now, that demand is not very high. They're at the very top, but it's something, and that's good. You'll see that their prices are still low. They're selling a lot. It's great. But now, let's say I deploy this for everybody. Suddenly, this one seller who was relatively new is now at the top in everyone's list. They're selling a lot. As they sell a lot, what are they going to do? As demand increases, they're going to increase prices. Right. So if there is any strategic response from sellers, if sellers, in some ways, you might say that if prices or what we call like equilibrium variables, like prices or reviews and so on, are a function of the position, that's automatically going to cause interference. So essentially, these naive estimates of a ranking algorithm's performance based on A/B tests are likely to be biased. And the main reason the main takeaway here is that the A/B tests are unable to simulate what the counterfactual market equilibrium would look like in terms of prices or availability or the distribution of this demand when a test algorithm is deployed 100%. So that's kind of the main insight. So the question is, what can we do about it? The first is, what are some existing solutions for interference bias in two-sided markets? And there are some existing papers which document the presence of this interference effect in other settings, not particularly this kind of settings. And what others have done is thought about how to modify experiment design to address this problem. And there have been ideas like double randomization or cluster randomization or thinking about counterfactual ranking. And these solutions, unfortunately, don't work at the ranking algorithm level. They work at the item level. For instance, if I want to understand an item here versus an item there, I can randomize this, the idea of double randomization. Cluster randomization can work in principle, but then you need lots of clusters, which are very similar. So you can do this by market, for instance. But then even though this was a pretty big platform we worked with, for instance, they didn't have very many markets. You just don't have the power to have so many markets to run this kind of an algorithm separately, because now your data, your observations are not in the number of observations, but in the number of markets. So our work essentially basically recognizes that these kind of solutions, these kind of experiment design solutions don't work for rankings in a marketplace environment. So we are going to leverage, what we're going to instead do is adopt what we call a bias reduction or a bias correction approach. Assume that the platform has already run a bunch of A/B tests, which they anyway keep doing. And we'll then look at this data and see how, based on both like a theoretical and like an empirical method, can we do something to reduce the bias in this, get closer to the true date estimates of what we would see. And that's that's our approach, because we can't think, apart from cluster randomization, which you need so much power, that we can't think of any other solutions which might help us here. So what I'll do here is show a theoretical framework, which will formally establish, I showed you this example, but I'll show you a little bit more generally, very intuitively, how we can establish the presence of interference bias in A/B tests of ranking algorithms. And then we'll try to provide now a solution based on what we call market equilibrium concepts. And then we'll apply this method to data from a travel website, and again show that interference bias exists there. And then we're going to build, based on this like theoretical model, we're going to build a customized machine learning model to predict the true date based on A/B tests, and then perform a counterfactual analysis to recover the true date and quantify what we call is bias here. So that's kind of the roadmap for the rest of the talk. Again, if something is not clear, feel free to jump in and ask questions. Any questions so far?
There's one in the chat actually.
Yes. Do the date estimators converge at the same rate in both scenarios? Sorry, I didn't get that question, because the date is biased in both. So there is no question of convergence because it's biased in some ways.
Right.
Does that answer the question?
Tanva, you can probably put that in the chat window if that is okay, or you have any other?
Okay.
Yeah.
Okay, I tried to answer it now, but maybe if it wasn't clear, whoever asked the question can maybe ask for further clarifications, and I can answer it again. But the fact is that it's biased. So there's, how it converges is really a function of the type of interference. And you will notice that our solution is kind of agnostic to the source of interference. So we're not going to worry about what is causing the interference per se, just that there exists interference. How do you fix it? Okay, so let me show you the state of a ranking algorithm A. So the measured date, so J here is, let's say, item. So this is demand of item J under algorithm A. So that is the superscript D basically just says it's demand. Q is for quantity. X is, think of this as hotel, or because we are using hotel setting here, travel website, I'm just calling it a hotel to fix some ideas. So these are hotel features that are fixed. Let's say like things like location of the hotel, the star of the hotel, and whether it has a pool or not, and things like that. Think of this as all the hotel fixed features. And now this is the distribution of positions of item J under algorithm A. So one thing we'll notice in data is that all these, under no algorithm is a hotel's position actually fixed. There is so much variation because of other things, because people might search for different dates, might have different family sizes, and might be low. So essentially what you see is a distribution of rankings for a hotel under an algorithm. And that P is essentially that. And this next P, superscript M, is a distribution of position of item J across all the algorithms. So if you not just had A, but had other things, so it's a distribution across all the algorithms. So what it's going to essentially we are measuring is that this is this variable under the A/B test. Whereas the variable that we are interested in is this. Notice that here, the last element in this demand is PJA and not PJM. So when A is the only algorithm deployed, it's the distribution of positions of this hotel under this algorithm and in the overall cohort of algorithms, which is just this, is going to be the same, right? So you can see, just looking at this very simple formula, that the measured Tate under A is not going to be equal to the true Tate unless these two quantities are equal. So item specific, the other thing we'll notice here is that item specific state variables like prices should not be included here because we think of these as equilibrium outcomes. What do I mean by equilibrium outcomes? Price is a function of demand, right? So as demand is realized, price will also be realized. If I'm selling a lot, maybe my prices will be high. If I'm always ranked in the bottom, then my prices will be low, maybe. So you'll see that even in our solution, we kind of assume that these are implicit rather than forcing them explicitly. And the extent of interference for item J then depends on the discrepancy between this PJ and PJM. That's kind of the key idea. So what we want to do is salvage imperfect A/B tests or detect where interference is more or less pronounced and corrected. And the metric we are going to use is the variation in the discrepancy of an item's ranking within a focal algorithm and its ranking in the overall cohort. And the idea is that items with low rank discrepancy are close to the true counterfactual equilibrium under the focal algorithm. So if you have, intuitively, you can think about this as if you have data across a series of experiments where we can pool these low discrepancy observations and learn data. So let me, in terms of theory, the way we actually show this theoretically, what we show is that you can actually exploit two types of variation in the data. If you have multiple cohorts of experiments, that is critical here. You need multiple cohorts of experiments. One A/B test is not going to be sufficient. That's kind of a key thing for this. So if there exist cohorts where hotel J's rank in an algorithm is similar to its cohorts ranking, then that is panel variation. Sometimes you might not have this, but you might have other hotels which are similar to this hotel, which have low rank discrepancy in some cohorts, and we can leverage that data also to identify the demand for J. So that was just like saying it in a very theoretical fashion, but I think the intuition is actually much, much simpler. So the intuition here is that let's say you have 3 A/B tests, right? And the first one, you have algorithm 1 and algorithm 2, which was exactly the example we saw earlier. So here you see that hotel B was actually ranked exactly where it should be in algorithm 1, also in algorithm 2. Now, in the next cohort, you see that in the next experiment, let's say you have a different experiment, let's say algorithm 3, hotel A's ranking has remained stable. It's exactly where it was in algorithm 1. Similarly, in hotel C and cohort 3, the ranking is where it should be in algorithm 1. So essentially what we are intuitively saying is that each of these hotels, we never see a full equilibrium for this data, right? We never see the full equilibrium of what would happen under algorithm 1. But we see portions of algorithm 1 in what we call a partial equilibrium in different cohorts. Now imagine that I can just take these blue portions of the data and kind of merge them together. That essentially gives me a measure of what the Tate would be if algorithm 1 was fully deployed. Right? As long as I see enough of these, essentially I can get an estimate of this. So we're going to pool essentially these low discrepancy observations from different cohorts, and that pooling will give us an estimate of the Tate. That's kind of what we are going to do. So what are some of the useful properties of this approach? The first is that, I think, and this is probably the most important, is that it's very agnostic to the source of interference bias. For instance, it really doesn't matter whether it's coming through supply constraints, through feedback loops. It can accommodate what we call both direct interference as well as indirect interference. And direct interference is things like where you might, and this actually happens in our data, where if I take the click-through rate, overall click-through rate of the algorithm of the hotel in the cohort and feed it into my algorithm's ranking, essentially it means that if I had another algorithm had ranked it very low, its click-through rate is going to be low, and a lot of firms actually do this, but that goes into my rank ordering. So my rank itself is endogenous. And as I change it, as I change this, then it's, and that's probably a more tricky situation than indirect effects like through prices or supply side constraints. So the approach is kind of agnostic to that. We also don't need to know the properties of the algorithms in the A/B test. So sometimes these type of solutions will rely on kind of backing out like the algorithm itself. So we don't try to do that. We just need to observe the eventual ranking distributions. And the nice thing from a practical perspective, rather, is this is not theoretical, but a practical perspective is that the platform does not need to change their experimentation kind of system. And this is generally useful because most digital platforms I've talked to or worked with have these things in place, and asking them to change their experimentation system is a big thing and usually a non-starter. So these are some of the advantages. As I said, the key requirement is that we need data from multiple cohorts. Without that, the method won't work. So you can think of that as a requirement or a drawback, or however however you would like to phrase it, but that's necessary condition in some ways. Okay, so that was the broad idea of the method. Let me now talk about the setting and the data and show you how we actually apply it. So the setting is a large hotel booking website where essentially hotels go, query location, travel dates, and they're shown a rank ordered result with like hotel A, B, and C. They can click and then go ahead and book. It's a pretty reasonably large website, not too huge. And we have data for over a 6-month period with like over 43 million queries, 20 million clicks, and about 900,000 bookings over a pretty large set of hotels. And for this website, the main source of revenue is commissions on booking. So whenever there is a booking, they get some commissions. So from their perspective, it is really important that they come up with a ranking algorithm which will actually lead to clicks and then bookings. So they actually played with a lot of, they ran lots and lots of field experiments on different algorithms. And our goal here, when there was one algorithm, which was kind of their main algorithm of interest, and we call it Genesis. That's just a name, no rhyme or reason why it's called that. And this algorithm was kind of their main algorithm of interest, and they tested it across many other algorithms over multiple cohorts, or approximately over 16 experiments over the 6-month period. And however, they never scaled it to 100%. So we never see it scaled fully. So what we are seeing in the data is a series of contaminated measures of state of this algorithm under different A/B tests. So here is just a little bit of data here. And what you see here in the bottom portion is the Okay, so the top portion, let's start with the top. The top portion essentially is a portion of queries allocated to the Genesis algorithm, because they also are, it's basically think of these as multiple A/B tests. What I'm showing you is a portion of queries, portion of traffic going to Genesis. And this is at a daily level, and these like dotted lines are where a new A/B test starts. So they just continuously run A/B tests. And you can see that, they allocated it from anywhere from, close to 95% or 85%, all the way to 60% and 80% and so on. And correspondingly, what you see in the bottom is that is the click-through rate of the Genesis algorithm across these cohorts over time. And what you see, and this last 2 cohorts, I think are particularly interesting because they ran for the 2 longest period of time in the data. You can see they're pretty long, these cohorts, compared to the other cohorts. But what's kind of even more visible is that there was a big discontinuous jump in how much traffic was going to Genesis, which went from about 60% to 80%, you can see. And what you also see is a concurrent drop in the performance of Genesis. right? So when lot more traffic got, so essentially they saw Genesis is doing well, they scaled it up, and then you can see that the performance dropped. And this is simply because of this, intuitively because of these reasons I was telling you about. And you generally see it, like when you scale. This is a big problem for many firms in this space. They come up with algorithms, they test it on a small sample, they think it's doing great, and they start scaling it up, and then boom, the algorithm is not very good. So this was just like some visual evidence. And what I wanted to talk was a little bit more, formally about these last two cohorts. So in addition to this Genesis, they were also testing two other algorithms. Let's call them algorithm 1 and 2, which were tested in both the cohorts. And what you see is that these algorithms, their performance did not change as much. It's only Genesis which kind of dropped precipitously, right? Because one question you might have is that this discontinuous drop can be attributed to platform level changes. Maybe it was holiday season and bookings just dropped for everybody. It was the end of holiday season, or something else happened. There was competition, or macroeconomic factors. So essentially what we do is that, because we have these other algorithms as well, we first run a very simple diff and diff model, where we model daily click-through rate and also the booking rate, and rule out what we call demand and platform side changes. So that, so we essentially just interact the last cohort into Genesis, and we see that there was a negative effect, even after controlling for the other algorithms' performance in the last cohort. So it's not so much that the other algorithms, it's not so much that something changed in the platform fundamentally that the performance of Genesis dropped. Okay, so next question you might ask, is interference really the culprit? Okay, we can see that something is causing this thing to drop. Is it really interference? So you can say that if interference is the root cause of this, then the bias should depend on the extent of discrepancy between the Genesis rankings and the rankings assigned by the mix of competing algorithms. So we kind of had this intuition from the theoretical model we had, right? That hotel A, for example, in this example here, has high ranking discrepancy, and therefore hotel A should, in a setting like this, hotel A should actually, our prediction should be further from reality. In some way, should have high interference, whereas for hotel B, there should be low interference. And what we can first therefore do is, first we define a simple discrepancy metric, which captures the discrepancy in a hotel's ranking in algorithm across from the overall ranking in a cohort. So this is the rank distribution of a hotel under algorithm A. This is the rank distribution of that hotel under the overall cohort. By cohort, I mean the experiment. And this is the, and we define it, and there can be many discrepancy measures. Here it's just a simple one, which is the expected ranking of hotel under algorithm A. And this is the expected ranking of the hotel under cohort C. Now, if these were exactly the same, it would become log of 1, because these would just cancel out if these were exactly the same. So the discrepancy would be 0. That's how we are thinking about it. Yeah. So, and if these numbers were different, for example, if the log term is 0.2, what it's saying is that J's average rank in algorithm A is 22% higher than its average rank in the cohort. So essentially, this is capturing how different these rankings are for this hotel under the algorithm as well as the overall cohort. So we then define this overall discrepancy across both cohorts, which is the maximum. And then we're going to look at all the hotels in the data and do what we call a median split. We're going to look at hotels which had a high overall discrepancy in the last two cohorts and a low overall discrepancy. And the key thing is that if a hotel has low overall discrepancy, the gate estimates will have less interference bias. So what I'm showing you here is now the performance of these, the click-through rate and the performance of these hotels by the median split, The red circles or the orange circles are hotels, or for hotels which have high overall discrepancy, and the blue triangles are for low overall discrepancy. And what you see is that the change in performance across cohorts is more pronounced for hotels with high discrepancy. You can see that these blue triangles are largely continuous across the two cohorts, but it is the orange circles which have dropped. So this drop is mainly driven by hotels with high discrepancy. And you can again show this formally using a diff and diff, controlling for things like hotel fixed effects, because that's not controlled in this picture. And you again see the same thing. Okay, so that was essentially reduced form evidence. Now, what I want to do is show you how we kind of can go about fixing it based on the solution that we had proposed. So first we define the state of algorithm A as follows. So we just, first we define the state on clicks, and then we'll move on to bookings, but it's very similar. So this is the total average treatment effect of algorithm A on clicks. So this is the portion of queries allocated to the algorithm on day T. And this is the probability hotel J receives an impression conditional on query. We have to model this because it's not that the hotels, as I said, there's always a distribution. It's not that each other hotel will always be shown. And that's going to be a function of whether what the query was, what the hotel features are. There might be some seasonality features which we have to take into account. And this is when the discrepancy features are set to 0. This is the key thing. The true, because we're predicting the true state, this is when the discrepancy features are set to 0. And you can have a similar model for when a hotel receives a clicks. And things like prices, rooms available, etc., should not be included here. Since they're equilibrium outcomes and not inputs, you can include them, but they're largely meaningless. So what we want to now do is come up with an objective function to model this for the number of impressions for hotel J on day T under algorithm. And we're going to model this as a binomial random variable. And we can write down the log likelihood that a hotel gets some number of impressions at the hotel day level as a function of all these features. And this probability in this binomial function can be modeled in any way that you want as a function of xj, gt, and this discrepancy. We are just going to model it using a feed forward neural network simply because it happens to work well. But even if you just wanted to use any other simple model, like a logistic model or something, that's totally fine. Depending on the setting, you can use what works well. So this is the architecture. Essentially, we feed these three things and we have a binomial loss function, and that's what we are learning. So in terms of features, we have hotel features, and we have a bunch of observable features, like things like the average impression share and so on. We also get two representation vectors based on co-occurrence of hotels in search results and clicks using a GLOB method, which many of you might be familiar with. And the idea is that for many hotels, we actually lack, because we have around 30,000 plus hotels which actually go into the analysis, we actually lack things like ratings, like star ratings, and many other things. And this GLOB method essentially kind of is a revealed preference kind of idea. Hotels which are similar get ranked similar, so we kind of get this representation vector from that. We also get seasonality features. Again, we do that, get this representation vector for day T based on top 5,000 destinations. And the reason we have to do this and not use day dummies is because we want to predict out of sample and not in sample, right? So how do I come up with a dummy for something I'm not seeing? And finally, for discrepancy features, we use the discrepancy metric we discussed earlier, but also other things like log ratios of deciles and not just the averages. Okay, before I jump into actually the results, I wanted to briefly talk about identification, which is essentially thinking about this theoretical idea that I proposed in the method, which we are now taking to data. Will it really work? For this to work, intuitively, if you recall, what you saw is that there was, in an earlier slide, I showed you that, let me go here. Sorry, this is useful. Okay, yeah. So you can see that for this method that I'm suggesting to work, I need to see these hotels B, A, and C in low discrepancy observations throughout the data. For example, if I never see cohort 2, I'll never be able to tell that hotel A, what hotel A's demand is. So essentially what I really need in some ways is sufficient observations which are at hotels which are at low discrepancy in at least one cohort. So what I'm showing you here now is the average discrepancy of hotels, and the maximum discrepancy across cohorts and the minimum discrepancy. And the last panel is the most important, because what it's telling us is that even though on average the discrepancy of hotels across from algorithm to cohort is very high, for almost all the hotels there is at least one cohort where the discrepancy is close to 0. And that's what this last graph is telling us. And that's what those low discrepancy observations are what will help us with identification. And similarly, for almost all the hotels, you can see this is the K nearest neighbor based on the hotel representation features. There are lots of hotels which are very similar to them. So even if you are not close to, you don't have low discrepancy observations, those hotels will have low discrepancy observations from which you can learn. And essentially what this is saying is that we have sufficient cross-sectional and panel variation to help us with this analysis. And this is again key from a theoretical perspective. I showed you the solution. From an empirical perspective, this has to be true in the data, otherwise the method is not going to work. Okay, so now that we know that we have enough data, we have the right type of data to be able to identify this, and we have the method. We essentially what we do is we're going to train and validate our model on the first 15 cohorts and use the last cohort as the holdout. And then we are going to perform the counterfactual analysis by setting the discrepancy features to 0, by assuming that the discrepancy between what's happened in the algorithm rankings and the cohort rankings are 0, which means that the algorithm rankings are the cohort rankings where it's fully scaled up. So, so here is the contrafactual Tate estimates, and what you see here is the the orange triangles essentially are the realized predictions. So you essentially what you are seeing is that orange triangle is what we see in the data, and what we see this blue dots. And you can see it's a distribution because we do this, it's a simulation, we do this multiple times. That's why you kind of see a variation around it and not a single dot for each data. And you see that that is different. So, and one interesting thing to notice here is, in general, when this algorithm is fully scaled up or close to fully scaled up, you can see that these two estimates start matching, which means that the algorithm is doing, the solution is doing pretty well in recovering this. And a good example is something like cohort 8, where the algorithm was deployed on about 90% of the traffic, and you can see it's largely similar. It's much closer than the other ones. Okay, so now let's go back and recall these last two cohorts. If you recall, that's when it went from 60% to 80% and the performance dropped. And when we look at the what our predicted take estimates say, you can see that even though this last cohort was fully pulled out, you can see that the predicted take estimates are pretty different from the realized ones. And in the realized ones, in the last cohort, we noticed that it went up to about 80%. And our predictions actually you can see that they don't predict high, they actually still predict low. So it's much more continuous and the predictions are close to the reality. So now that was just showing you again the pictures. If I have to actually compare the last two cohorts and do in a more formal way and define what we call relative bias, which is predicted take minus measured take divided by the measured take. And I'm showing you what the relative, I don't call it bias here because notice I never see the true take. So that what I have is my predictions and the measurement. So here cohort 16 was held out, so it was not in the data. And you can see that in cohort 15, when 60% of the traffic went to Genesis, the relative bias is around 15%. Whereas in cohort 16, when 80% of it went to the Genesis, the relative bias is -3%. And in fact, it's much lower. And importantly, it's also I mean, this also tells you something which I forgot to mention earlier, that it's very hard to sign the bias in some ways in these kind of settings, because especially when there are these feedback loops. So what we see is that there can be significant bias in the Tate estimates. That's one big thing if we ignore these problems. So you will really overestimate the performance of your algorithm in many settings if you don't account for the fact that these interference biases are happening. And finally, we also want to understand how it affects bookings, because I just showed you the model for click-through rate. You essentially just build a third neural network to model booking conditional on click and tack it on and estimate it. And that's what we do here. The effects are even further inflated because there is one more model in here, right? Which is again being misestimated. Here we see that the relative bias for the last two cohorts is about like 28% and 10%. And overall, what this is telling us is that these naive Tate estimates based on A/B tests can be significantly biased. And we saw that even just like eyeballing the data, right? It fell significantly when we scaled up the algorithm. And this kind of approach where we try to control for it and understand what it would be if we were to correct for it can actually help significantly with bias reduction. Okay, to quickly conclude, essentially in this paper, what we essentially identify is that A/B tests of ranking algorithms will be biased on almost all settings, and we try to provide a solution for bias reduction that is agnostic to the source of interference and can be used with existing data from a series of A/B tests. And we present a simple application where we show that this actually happens. This is not a theoretical concern on a travel website, and quantify the relative bias and its economic impact. And from a managerial perspective, for many of us who are often talking to these firms and working with these firms, I think, or teaching students, the main thing is to kind of convey that we should not naively interpret A/B tests of ranking algorithms, and that our Tate prediction algorithm, that if that's all you have, at the very minimum, you can use a method like this to actually correct for this kind of bias. And that's pretty much what I have. Thank you so much for listening so patiently. And I'm happy to take any questions.
Yeah, so thanks a lot. We have two questions in the chat, and then we can take Nikita's questions as well.
Okay. So at what rate do these estimators? Okay, that's a good question. We actually don't have an answer to that. And part of the reason is that we don't actually model the source of the interference in some ways. So I can't really say at what rate these estimators that we have in the paper will converge. What we can show is that these will converge. So we can show a bias kind of an argument, like a consistency argument. We don't have an argument on the efficiency of these estimators. That's a good question. And that's because unless we make a few more assumptions on somehow these things, it's hard to kind of show. And I mean, from a practical perspective, I think what you really need to show is that these are identified in the data, like those identification graphs that I showed you. Yeah, I don't have a good answer to the question of how they would converge in a general setting.
Right. Just one more question by Akshay. Is discrepancy in ranking the only factor that might affect Tate? For example, will the other attributes of competing hotels like star ratings, location, number of rooms also not cause bias in Tate? Are we assuming these hotels are the same kind?
Okay, so the way the model is, we write down the model, kind of fundamental in some ways assumption is that each hotel's demand is a function of its own ranking and its own features. In some ways, what we are doing is that we are splitting this in some ways, right? We are not writing a choice model where The user comes and then figures out which of these like 5 hotels to buy. And that's a critical assumption in some ways, because if what we are trying to do based on the picture that we had, if you notice, is we are decoupling everything, right? And then we are trying to put these back together. We have A from here, B from here, C from here, and then we're putting it back together. Now, if things within are all linked again, I can't do this decoupling. So in some ways, what you're saying is that a hotel's demand is a function of its own ranking, its own prices, and its own thing, and not things around it. And that's, in some ways, you can question whether it's a reasonable assumption or not. But the other way to think about it is without that, you can't have any solution. So you have to think about whether you want the solution, which might be somewhat imperfect. And you can see how imperfect it is in any empirical setting that you have. In our setting, we saw that it was mostly fine based on that holdout sample, but it may or may not be in other settings.
Nikita has a question. Nikita, do you want to unmute and ask?
Yeah. Okay, so it might sound silly, this question, but I was just wondering, why wouldn't a platform just fully deploy one algorithm at full scale and then compare it to another algorithm? I mean, is it because it's expensive, or there are cost constraints? Because doing this would essentially rule out the supply constraints that we were worried about, right? So this was something that just came to my mind.
Yeah, that's a good question. And that's something, they should generally be asking. In general, the reason we do an A/B test is because we are holding everything else constant, like the other supply side, the demand side factors, the macroeconomic factors, and so on. For instance, doing an A/B test where we run this today when, inflation is so much higher and lots of things are going on in the world versus like 2 months or 3 months back when something else was happening. Those two are not valid comparisons. So the reason that's one main reason we do A/B tests, right? Where we hold all those things constant and then we see how the performance of this algorithm is compared to other algorithms where everything else is held constant. If you do it over time, across time, we are not holding those other things constant. So it becomes harder to see whether it is the algorithm or whether these other factors. That's why they generally don't do it. That's the whole reason why we do A/B tests. And more practically, the reason they are always hesitant to always scale it up is that usually, if you are a data scientist or an engineer, you came up with these kind of algorithms, you tinkered with it, you have some models, you came up with it. And then it's very hard to convince like somebody senior to come and say, okay, now I've come up with this algorithm, you know what, like now deploy it 100% on the website. It's a pretty big decision to deploy something 100% on the website, especially something as big as this, which will hit the revenue tomorrow if you hit. It's not a small change somewhere in the website. This is like their fundamental driver of how they make money. If this was messed up somehow, their traffic would fall, their revenues would fall. So they're not going to have buy-in to deploy these things immediately. They will have to demonstrate that this works compared to what already is in place. So it's both a practical as well as an important business consideration and also theoretical reason that I mentioned. That's why I can't come up with an algorithm and say, hey, you know what, to test it, like let's deploy mine for a week tomorrow, for starting tomorrow. That's usually the main reason.
Yeah, okay, makes sense. Anuj sir, I just had one more question if I can ask.
Yeah, go ahead.
Yeah, okay. So you already said that we sort of collate all the low discrepancy items in every cohort, right? So I was wondering, why are we calling them low discrepancy? Because in some sense, because they're ranked across all the algorithms on the same level, they don't have any discrepancy, right? I mean,
yes.
Do you get so why are we referring to them as low discrepancy items? I mean, are there other sources of interference?
No. So they are low discrepancy. But what I mean by low discrepancy is if you look at how I wrote down that like neural network model, it's at essentially the way it's learning the model is at different sets of features and different levels of discrepancy. In some ways, and then in the contrafactual, we set the discrepancy to 0. But if you're if the way to think about it, if the impressions are independent of instance positions, let's say that people just searched throughout, like people looked at everything from rank 1 to rank 20 and clicked on everything almost equally, then the discrepancy will not have such a big impact. So essentially what that neural network is learning is, as the discrepancy changes for different hotel features, how the impressions or clicks are changing. And in some ways, what we are looking for in the counterfactual is the limit where the discrepancy approaches zero. And that's why I call, so it's learning not just from the zero discrepancy observations, it's also learning from other discrepancy. And it's kind of figuring out how it changes. That's why I call it low discrepancy, because it's kind of learning and then like taking it to the limit in the counterfactual.
Okay, thanks. Yeah, makes sense. Thanks so much.
No worries.
There's just one last question if we can take. This is does the hotel search screen have filter options that might show different ranking results with the paper account?
Yes, so that is to the extent that I think that we can take into account. In some ways, we are kind of agnostic to that, because it goes under, if I filter by price, let's say I just show, I have one algorithm and this algorithm is somehow not great, people always end up going and filtering by price. And that will be in the distribution of rankings that we see. Essentially, what we care about is that the distribution of rankings is somehow different under these two sets. So it's in some ways agnostic to whether people are filtering or whether this rank distribution came because the hotel itself was, the system itself was doing it, or somehow this algorithm is poorly specified. As a result, people end up doing some filtering themselves.
Okay. I think we don't have any more questions. Thanks a lot. Once again, I have already shared the paper is on SSRM, so I have shared it with the seminar.
Okay, great.
Beforehand. I can't thank you enough for taking out time. It was really
Thank you
great.
so much for having me. This was very enjoyable.
Thanks a lot.
Thank you again for all the questions and for coming to the seminar. I know late in the evening, people want to go home and get dinner and do more fun things. So thanks for doing this, and look forward to seeing you all sometime in person.
That's great.
Thank you.
Thank you so much.
Bye.
Thank you.
Bye.